We've learned how to do the basics of Lewis dot structures so that we get an octet, which is stable, or 2 electrons on hydrogen. Now what we're going to do is look at some complications to this.
What if the species has charge? A polyatomic ion. Well, charge means that electrons were either lost or gained. If you have a negative charge, it means that extra electrons are put into the valence shell of the atoms in the Lewis dot structure. If there's a positive charge, it means electrons have been removed from the valence electrons. So to do Lewis dot structures of polyatomic ions, what you need to do is count up the electrons in the valence shell of all of the atoms in the polyatomic ion, and then adjust the number of electrons based on the charge. So now what I'd like you to do is to do these 2 polyatomic ions, chlorate and ammonium, and so pause the lecture now and then resume it after you've completed these 2 problems. To do chlorate, the first thing we do is we count up the valence electrons in the chlorine, 7 electrons, and then we have 3 oxygens, so the number of electrons is 3 times 6 electrons for oxygen. Charge adds 1 electron to the total. Because it's a -1 charge, 1 electron has been added. If the charge had been 2 negative or 3 negative, well then you would add 2 electrons or 3 electrons. This gives a total number of electrons as 26 electrons. Notice it's even. Lewis dot structures that we will be doing will always have even number of electrons because electrons will be in pairs. So we go ahead and we place the bonding electrons in, and then we add the non-bonding electrons until we have used up all electrons, but we have not used any extra electrons. Only the electrons are there. Now, chemists tend to be very freaky about charge because charge is very important. The behavior of things is highly dependent on their charge, whether neutral, positive, or negative. So what we always do to a polyatomic ion Lewis dot structure is we put brackets around the Lewis dot structure and then put the charge on the outside to emphasize that it is a charged species. To do ammonium, we count up the electrons for the nitrogen. There's 5 electrons in the valence shell of nitrogen and 1 in each hydrogen, so it's 5 plus 4 times 1. Charge removes 1 electron, so the 9 electrons have 1 electron removed from them to give them a total of 8 electrons in this structure. We draw the skeleton and then place electrons in the bonds, and you can see all of the electrons are used up just to form the bonds. Then what we do is we put brackets on it and give it a positive charge. Sometimes the number of electrons is less than everything to have an octet and hydrogen to have a pair. Sometimes we have to find some way to give an octet to each atom without adding more electrons in, yet making sure each have 8. In order to do this, we do something, we share another pair of non-bonding electrons, or we say we share a pair. The way that we do this is we identify the atom that does not have an octet, then we move to an adjacent atom that does have non-bonding pairs. We take one of the non-bonding pairs and move it between the 2 atoms. We repeat this until we have a stable structure. However, don't get carried away and just keep sharing pairs until you have a very strange looking structure. You stop as soon as you have an octet on everything. Here's an example, the carbon monoxide that we couldn't form by just squishing atoms together. We can now try to do this by sharing a pair. Carbon monoxide has 10 valence electrons in it. I start with putting a pair of electrons to form a bond between the oxygen and the carbon. I then place remaining non-bonding pairs on the structure. but I must stop when I run out of electrons. You can see there are 10 electrons in this structure, and I don't want to have any more, but I do not have stability. So what do? I see that carbon does not have an octet. So I move to the adjacent atom, oxygen, and I take a non-bonding pair and I move it between. I repeat this until I have stability. And once I have an octet on carbon and an octet on oxygen, I then stop because now I have stability. Now what I'd like you to do is pause and do these problems. You may find that you have to share pairs of electrons, extra pairs of electrons in these structures. So remember what we do is you find the atom that does not have an octet, you move to an adjacent atom that has non-bonding pairs, and then share one of those non-bonding pairs between those two atoms. The first thing that you do is you draw your basic Lewis dot structure by counting up the total number of electrons, 6 on sulfur and 6 on each oxygen for a total of 24. On the skeleton you place the bonding pairs and then you place the non-bonding pairs. Now your skeleton might have a non-bonding pair missing from sulfur and on this oxygen that doesn't have a non-bonding pair, and that's fine. It doesn't matter what your intermediate structure is, it matters what your final structure is. If I look at this, I can see that sulfur, the oxygen on the right and the oxygen on the bottom all have octets, but the oxygen on the left does not. So what I do is I take a non-bonding pair. Remember, you go from the atom that does not have an octet to an adjacent atom with a non-bonding pair. You take a non-bonding pair and you move it between. When I do that, you can see there is now a double bond between the oxygen and the sulfur, on the oxygen on the left and the sulfur. It doesn't matter which oxygen the double bond ends up being there. The whole thing is that the sulfur has 2 single bonds to 2 oxygens and 1 double bond to 1 oxygen. So you should have a sulfur with a double bond and a single bond and another single bond on it, 2 oxygens with 3 non-bonding pairs and a single bond, and then 1 oxygen with 2 non-bonding pairs and a double bond. Okay, to get to this point, what did we do? We took carbon, which has 4 electrons in the outer shell, 3 oxygens, each with 6 electrons in the valence shell. So that gives us 4 plus 18. That's 22. There's a charge of 2 negative, so that means that we have to have 24 electrons. The 2 negative puts 2 more electrons in there. I place 6 electrons, or 3 pairs of electrons, as bonding pairs, and then I add in the remaining electrons as non-bonding pairs, but I stop when I get to 24 electrons. Now you can see that the oxygen on the left is not stable. It does not have an octet, so we go to the adjacent atom that does have a non-bonding pair and move it between. This gives us a structure that is isoelectronic with the sulfur trioxide. Again, it doesn't matter where your double bond is. It can be between any of the oxygens and the carbon. The key thing is that you have on carbon a double bond and 2 single bonds, and the oxygens, 2 of them are going to have 3 non-bonding pairs and a single bond, and 1 oxygen will have 2 non-bonding pairs and a double bond. Don't forget that you need to have that bracket with the charge on it for any polyatomic ion. You must show charge in your Lewis dot structures when there is charge. To do this problem, again, we start with our skeleton, putting carbon in the center. We count up our valence electrons, 4 from carbon, and then 6 from each oxygen. That gives us 16 electrons. We place electrons as bonding pairs between the carbons and the oxygen, and then start placing the electrons as non-bonding pairs on the other atoms. You'll see that we run out of electrons and the carbon is not stable. You may have put your electrons all on the carbon and one oxygen, and that's fine. Again, it doesn't matter what the intermediate structure is, it matters what the final structure is. Now, with this structure that I've drawn here, there's a lot of options for how we can share electrons. I could go from the carbon, which is unstable, to the oxygen on the right and take two non-bonding pairs and move them in. I could take the electrons that are on the left oxygen and move them between to share. Or I could take one pair from each oxygen and move them in. There's a lot of possibilities. If I'm going to show you all of what all of those possibilities would look like, and you can see here there would be a triple bond between the carbon and oxygen on the right, or a triple bond between the carbon and oxygen on the left, or two sets of double bonds. These structures are all considered good Lewis dot structures. If you were going to be going into this in a little bit more depth, we'd talk about resonance structures here and what they mean, but we're not going to worry about that, and we're just going to accept any structure that fits the rules of being stable, that every atom has an octet, and that hydrogen only has two.